Welcome to Lecture 28, entitled Stokes theorem. And so here we're going to be looking at an application in 3D. This lecture basically is covered in material from reading assignment 5, that's sections 4.2, which deal with cylindrical geometries, section 4.6, and additional problems in section 6. The objectives here are to apply the Stokes theorem for magnetostatic problems. And the concepts and visualization skills are determining the direction of the field and the functional dependency of the field's magnitude, and developing the procedure for determining the field for a cylindrical symmetry example. As usual, the second slide is just an outline of the slides to follow, so we'll just skip over this slide. Okay, so I'm going to use a magnetostatic example. This is for a source-free field. And so these are going to be basically fields which are homogeneous, involving homogeneous media. And so that just means that these are constant values and don't depend on position. So we can either describe this problem in terms of a magnetic field or a magnetic flux density. If we describe it in terms of magnetic field, then we have one equation with a curl, one with a divergence, with a J subscript E. This is a current flux density, or we could express in terms of the magnetic flux density, in which case would be curl of B equals mu times JV, which is the current flux density, and divergence B is equal to 0. In our case, basically, we're going to work with the H version, which means we're just going to let H be equal to F to just sort of have a consistent set of symbols. And we're going to just let J of subscript E just be J. So this will be a current flux density. F in this case will represent the magnetic field. And so if we take this nomenclature and then apply Stokes theorem, then effectively on the left-hand side, this is a closed contour integral. And this is related to taking the curl of the vector field times the dot product of a differential surface area vector enclosed by this contour. So the surface area can take on any shape. In fact, it's advantageous because we can then choose the surface area and the curl of a vector field to be more or less in the same direction, so as to make this computation as simple as possible. Now, the curl in this case is equal to J, so that means we can just replace this by J, and given that J is a given, means that the right-hand side is the part that we'll be doing, where we do the real calculations. And the left-hand side will basically, we're hoping to somehow extract F out so that we can compute the value of F. And so symmetry will allow us to do that. So the problem statement we'll use here is to consider a cylindrical rod of infinite length with radius capital R and its axis of symmetry aligned with the Z-axis. And the rod has the following current flux density distribution. For 0 is less than R is less than capital R, the field basically, the current flux density is pointing in the z-hat direction, and J0 is a constant value. Once you get outside of R, capital R, then there is no current flux density. And again, it would be in the z-hat direction. Again, R is the square root of x squared plus y squared. So this, given that it's cylindrical symmetry we're going to be dealing with, and we just choose to basically express everything in terms of cylindrical coordinates. All right, so what's the calculation procedure to compute F? Well, it's very similar to what we did when we looked at calculating problems in which we were dealing with irrotational fields. The only difference is you apply Stokes theorems rather than the divergence theorem. So the first step is to determine the nature of the symmetry and determine if you need to use superposition. Second is to establish the form of F and establish the shape of the closed contour. Thirdly, compute the left-hand side of Stokes theorem, then the right-hand side of Stokes theorem, and then finally equate the left-hand side and right-hand side to compute the value of the vector field F. Note, the procedure here is almost identical to problems that invoke the divergence theorem. All that changes is that the choice of an open surface, which is bounded by a closed contour. And so now we're dealing with surfaces, open surfaces and closed contours, whereas before with the divergence theorem, we were dealing with closed surfaces, and we're talking about bounded volumes. Okay, so let's look at basically establishing the symmetry and whether or not superposition is required or not. So there's an interactive module that you can make use of here. Let me just explain what these different sliders represent. So slider T is the observation point, which is this blue dot that you see here, on an expanding red circular ring. So this ring, when it expands, the blue point goes with it. Slider S is selecting different current flux density pairs, this one and this one, on the circumference of the blue cylindrical shell, which is this cylindrical shell that you see here. And they are equidistant with respect to the observation point on the red circular ring. So for instance, the distance from here to there is the same as the distance from here to here. Slider P is circumferential movement of the filament pair in opposite directions around the blue cylindrical shell, which just means basically if this moves in this direction, this moves in this direction. So the distance between the observation point and this current flux density and this one will always be the same. So you basically can go all the way to the back where they essentially coalesce, or they come to the front where they coalesce. And so what we're doing basically is mapping out pairs, and we can use that to determine the complete distribution on this cylindrical shell. You can then choose to reduce the radius of the shell and do the same thing over again. So in effect, what we can do is map out the whole region of current flux density by just considering basically two current density, flux density filaments, and these filaments basically are equidistant with respect to the observation point. And so this is now just a description. The horizontal blue arrows, which you see here, are the field contribution from each current filament at the observation point. And the vertical blue arrows, which are these ones, are the current filaments that are equidistant with respect to the observation point. This distance is the same as this distance. And the red circle is a closed contour on which the field is uniform. And we'll essentially show how that's possible. Horizontal red arrow is a net field due to both filaments. So if you'll notice here, if I move these filaments back and forth, I will always have these two vector fields basically producing a component of field which only has a circumferential component. If I were to move these around and look at different points along here, the picture will always be the same. The arrow will always be pointing in a circumferential direction. Also, along a ring, the picture never changes, so that means the field at every point along this ring will not change. On the other hand, if I move this circle out to further away, then the aspect ratio that I see is changing. So I would expect the magnitude of the field on a given ring to depend on the radius of that ring. So effectively, this allows me to determine the symmetry, and therefore I can put together a general expression for the vector field where the magnitude of the field is the unknown, but the direction is known. All right, so now that we have set the groundwork in place, we can basically determine the equation of the field F, and we can establish the shape of the closed contour. So we know that F has circumferential symmetry. That means the field lines form closed circles, and that the field depends on the radius. In other words, how far you are out from the axis of symmetry. And so if you look here, for instance, F is a function of R being square root of x squared plus y squared. And this basically just represents a circumferential direction. Now there are two possible orientations, clockwise and counterclockwise. So this basically can only take on a positive value since R is greater than 0. And so F either takes on this form or it takes on this form. So this and this are related to each other only by the fact that this is being multiplied by -1 throughout to obtain this expression that you see here. Again, so just a note, the direction was determined using the right-hand rule. Since J points in the z-hat direction, F must point in the theta-hat direction. And so effectively, that's how we got the result that you've seen above. Just as a note, you might want to memorize a Cartesian form of the theta-hat vector, which is the one that's displayed here in orange. All right, so now what we need to do is to create a closed contour. And this closed contour is associated with Stokes' theorem. And so since we know the direction of the field, we can basically then determine how to choose the contour. And the criteria typically that are used are the ones that are stated here. So one possibility is that the vector field F is parallel to the tangent vector on a contour segment, and magnitude F is constant at each point on the same contour segment. Hence, f dot ds is either the magnitude of ds or minus the magnitude of ds. And the magnitude of f can come outside the integral. Since we're integrating dot product between the field and the tangent vector, right, that means basically if the field can come outside, then we've got everything we wanted, and that was to somehow remove f from the integral sign. So that's one option. The other option is the vector field f being 0 on a contour segment, hence f dot ts ds equals 0. And thirdly, the vector field f is perpendicular to the tangent vector on a contour, hence the dot product equals to 0. Now these latter two generally occur when we're dealing with a contour which is comprised of multiple segments. In the case of cylindrical symmetry, typically we just have one smooth contour. And so it's this criteria that generally applies. All right, so given this, the solution is to create a cylindrical contour with a variable radius r centered on the axis symmetry of the cylindrical rod. And so, as I said, the left-hand side of Stokes' theorem is the contour integration, closed contour integration of f dot t ds. And we mentioned that the different options are that f is perpendicular to ts, f is parallel to tds, or f equals 0. In our particular case, it'll be this option, which applies. All right, so this is just an interactive visualization of the closed contour. And just an explanation, the slider T is an expansion of the closed contour, which is this blue cylindrical ring that you see here. That radius gets larger as you play with T. The vector field F, which is yellow, it's just basically circular, and again in a direction of theta hat. The current flux density, which are these blue arrows that you see, and the area S enclosed by the contour. So that's this red area. So the contour is in blue, and the red area is the surface area. I can also do a trace, where essentially I'm just cutting through and looking down on the XY plane. For this particular case, I'm just showing inside the contour. So for instance, if this exterior shell is basically as far as the current flux density goes, these dots represent the direction of the current flux density pointing out of the page, which is in the z-hat direction. This NDS would represent the area vector that's basically associated with this planar area. This is the radius of the contour, and this TDS basically is the vector that's tangent to the closed contour. So in this case, this contour is only basically taking a portion of the total current flux density, because it's only encapsulating a fraction of the total surface area. So let's just quickly look at what these are. Black dots are the current flux density out of the page. The differential area vector NDS is out of the page, and the red circle is a closed contour with radius r, and tangent vector TDS, it's a contour that bounds the area shaded in red. Now, just a mention, we'll come to this again. So we've chosen basically, we know the direction of J, we know what the direction of F will be, but you can use the right-hand rule basically to assume a specific direction for the surface area vector, and it's convenient in this case to use a planar surface because J is uniform across the planar surface. So in this case, that would be choose NSDS to be in the same direction of J. If NSDS in the same direction of J, then again by the right-hand rule, the fingers will point in the direction of TDS. So this is direction of TDS. Direction of NDS is out of the page. That's consistent with the right-hand rule. And so more or less we're all set to go in terms of doing the calculations. Okay, so we're going to now compute the left-hand side of Stokes' theorem. So this is just again summarizing by the right-hand rule. If the thumb points to the direction of the z-hat, direction of ds, and the same direction as j, then the finger points in the direction of the unit vector t, which is counterclockwise in the xy plane. The field in our example points in the same direction as unit tangent vector t by the right-hand rule. Note, we could have chosen the thumb to point in the minus z-hat direction, in which case the unit tangent vector t would have been clockwise. The direction of J would remain the same, and F would still remain counterclockwise. You can work this out as an experiment if you wish. I chose it this way so that all dot products produce positive quantities. Okay, so my field takes on this. It's counterclockwise, you can see, and the radius basically is just the square root of x squared plus y squared. Okay, so I'm going to have to parameterize the contour. I need to know what TDS is. So basically we choose x to be r cosine theta, y equals r sine theta. Z is equal to 0 in this case. We're just basically on the xy plane. 0 is less than or equal to theta is less than or equal to 2 pi. And so r in this case will be just r cos theta sine theta 0. We need TDS, so next thing we have to do is take the derivative of r with respect to the parameterization variable, which is basically theta. So this just becomes minus r sine theta, r cos theta 0. TDS will just be r dot d theta, and so this is the expression, and this in fact is counterclockwise by convention, so we don't have to multiply negative sign. We now basically have to also compute what the field is in cylindrical coordinates, based on the way we parameterize the contour. So x gets replaced by r cos theta, y gets replaced by r sine theta, and these are substituted in this expression to finally give us this expression for f. And so now we can go ahead and do the computation. We can substitute for f, we can substitute for TDS, and do the closed contour integration. All right, so now that we have computed the vector field f and the tangent vector TDS, we can make the substitutions. And so if you look here, this is basically the result of f. F of r can come outside because basically it does not depend on theta. And this represents the vector TDS, which is the tangent vector. And you take the dot product between these two. Sine squared plus cos squared will give you 1, and you're just left with an r. And the integration then, therefore, is from 0 to 2 pi, and this just becomes 2 pi r f of r. Now you'll notice that this is, of course, what we're trying to determine. It's the scalar function, it's a function of the radius. But 2 pi r is the circumference of the circle, which was the contour that was chosen. Note, for other geometries, the left-hand side is computed once and remains the same. And so what I've shown here is a summary of the different cases. So for the planar case, which is an infinite plane, we can have, for instance, various combinations. I've just chosen to show you 3 here, but there are other combinations as well. So for example, direction of f and j, if f is parallel to the x-hat vector and j is parallel to the z-hat, right? And then the left-hand side of Stokes' theorem will take on this form. So it'll be a function of y times x. X is the length of the contour segment on one side, and f2y dot x, f2y being on the other side of the contour. Again, in this case of planar, the contour will be a rectangular form, so there'll be 2 sides, basically, which have to be computed. And so this would be the case if you have f parallel to x hat and the current flux density parallel to z hat. You could also have this combination, f parallel to y hat, j parallel to x hat. In this case, the scalar function is the function of z, and the contour segment's length would be y, and on the other side of the would be f2 of z, again the same contour segment. So 2 sides basically have to be determined. And a third option we've chosen here is f parallel to z hat, j parallel to y hat. So in this case, turns out that the scalar function is a function of x times z being the length of the contour segment, and then on the other side, be f2 of function of x, again basically a scalar function to be determined, times the z, the length of the contour. So these are different cases to be considered for the planar geometry. Another example would be the toroid, which is just a donut. In this case, the current flux density encircles the donut. So a trace in the xy plane would indicate that the current flux density J is either in the z hat or minus z hat direction. So effectively what you have is the wires poking into the page or poking out of the page. And F, again, according to the right-hand rule in this case, is going to be in the theta hat direction. The left-hand side under these circumstances would be 2 pi r, f of r, where this is a function to be determined. And you'll notice here then again that r is the radius of the circle parallel to the xy plane and centered on the axis of symmetry of the donut. 2 pi r again is basically the length, the circumferential length of the contour. And then we have a solenoidal case where basically J is in the theta hat direction, so you have an infinitely long cylinder but the current flux density basically is in the circumferential direction. In this case, basically, left-hand side of Stokes' theorem would be some constant to be evaluated, times z, where z is the length of the contour segment. In this case, would be along the z-hat direction, and 0 otherwise. 0 meaning outside the actual cylindrical shell. Another case is the cylindrical case. In this case, J is in the z-hat direction. That's the current flux density. In this case, we find on the left-hand side that we get 2 pi r times f of r, of course being the scalar function, which needs to be determined. And 2 pi r is just the circumferential distance around the circular contour. And again, r is the radius of any circle centered on the axis of symmetry of the cylinder. So just a note here, if the contour is rectangular, which is the case if we're dealing with a planar or solenoidal case would be J in the theta hat direction, then there are 2 contributions on the left-hand side. And so typically you have to solve this problem where either one side is known, which would be the case of the solenoidal case, or in the planar case, you first have to determine basically what the field is outside on both sides of the slab. And once you've determined that, then you can use one of those as a condition. So for instance, you'll be able to solve for Fy. Once you know Fy, then you can solve for F2y, which would be, for example, inside the slab. All right, and just I made a note of this. Note 2 other combinations for the direction of F in the planar case have not been mentioned, but you can look at those as well if you wish. All right, so now we do the computation of the right-hand side, which would be just to integrate the current flux density times the differential dot product with the differential surface area vector. Well, we've chosen the differential surface area vector to be exactly in the same direction as the J, so that make this as simple as possible to compute. And so we know what J is, but we have to be careful now because when integrating, we know we have a discontinuous function. So we have a region in which the current density was a constant and a region where it was 0. So we have to consider 2 cases. The first case is for radius less than capital R, which is the exterior perimeter radius of the cylinder in which a current flux density exists, and then exterior to that region. So in this case, J dot ds would be, and this we've just done in Cartesian coordinates, J is 0, 0, J naught, which is in the z-hat direction, and nds will be just 0, 0, 1 dy dx. This is basically pointing in the z-hat direction. This is the differential surface area vector. If you do the computation, the dot product, this is just J naught dy dx. This is in Cartesian coordinates. You're integrating over circles, so the upper bound would be r squared minus x squared. Lower bound is minus square root of r squared minus x squared. Value between r and minus r. So again, this is r is a free parameter, and that's valid up to a value of r equals r. And so we basically have written it out in this fashion. If you integrate, this is just pi r squared J naught. So this was basically what the right-hand side would be for this region. And for the region greater than r, that means basically that you would be using the same expression, but r would be basically replaced by capital R, because for any r greater than r, there's no additional contribution to the integrand since J naught equals 0. So outside of r greater than, for r greater than r, the integral of the current flux density, which is basic of the over the surface area, which is just the current, would just involve this little r being replaced by capital R. And if you do this computation, this becomes pi r squared J naught. So these are the 2 different regions to consider. And here you can see, for instance, this is what the contour would look like for the case r greater than r. And you can see here it encapsulates the total current flux density. And of course, in this region, there is no current. So there's no contribution being made in this region, but you're encapsulating the total current just because of this area here. Here, we're only seeing a fraction of the total current. All right, so now we equate the left-hand side with the right-hand side to compute F. So for instance, here's the left-hand side, here's the right-hand side. From previous slide, here's the left-hand side. From the previous slide, here's the right-hand side. Similar for r greater than r, the left-hand side never changes. The right-hand side took on a different value here. So here we need to compute now what f of r is. F of r will just be J naught over 2 times r, so it's proportional to the radius. And outside r equals capital R, it will be inversely proportional to the radius. We know that the field is in the theta hat direction, and so this is the magnitude of the field, and F would have this value for r less than capital R, and would have this value for r greater than r. Now you can also make things a little simpler. We know that, for instance, that if we integrate the current flux density over the full surface area, which is more or less the calculation you see here, this is more or less the same as saying the total current, I, that's flowing through the cylindrical rod. So you can express these fields in terms of the total current rather than J naught if you wish, because total current is something you actually physically measure. If we do that, then these expressions can basically be reformulated, and you end up with something that looks like this now. And clearly here is where the I shows up, and then clearly here the I shows up. All right, so finally we'd like to graph the results. So this is just the magnitude. And so you can see for r less than r, it has a linear ramp. And we just use these specific values just for sake of illustration, J naught and r. And once you get r to r equals r, then beyond capital R, it has a 1 over r dependency. And so this is basically then gives us the whole, the field over the full region. All right, that concludes lecture 28. Thank you for listening.